This is the 2019 Discrete Further Maths AS paper. So this is network flows. To draw these cuts, well, I mean, it's already drawn, but if it's not, then you just want to have whatever's here on one side and whatever's here on the other side. And you're only looking at what's going from the source side to the sink side. Okay, so we've got 10, 9. This is not going from source to sink, so ignore that. So you've only got 10, 9, 7, and 5. And if you add them up, you apparently get 31. Here, activity networks. So what is it asking? Which of the following statements about D is correct? Well, if D is a critical activity, which it says it is, then it must have no float time. And if for it to have no float time, it must start, and then after its duration, it must end after 10 plus D, right? After 10 plus D hours, days, or whatever it is. So D must be 10, right? Because if D was 10, then it would have no float time, and so it would be fine. This is linear programming. Okay, so the first thing you want to do is just define your variables. So let's say X is the number of apple cakes and Y is the number of banana cakes. We want 3x plus 2y, looking just at the x, to be at least 36. Okay, you can use 36 or you can use less, whichever optimizes it. Okay, and now looking at the flower, we have 100x plus 150y being less than or equal to 1500. You don't necessarily have to use 1500, so that's why it's less than or equal to. And then finally, just the basic things: x and y are both greater than or equal to 0, and x and y are integers. You can also put. Now, the objective function is the function which you maximize. Okay, sometimes it's called p, sometimes it's called z, I think. Anyways, yeah. So you just want to specify whether you're maximizing or minimizing it. We're going to maximize x plus y because we want to have the most number of apple cakes plus banana cakes. State the definition of a bipartite graph. It's basically one where your nodes are split up into two sets, and edges can only cross from one set onto the other set. Okay, and they can't cross across that set, across the same set. So you can just read this definition here that I've put. Here, draw a graph to show which musicians know how to play which instruments. Here, I would just write down their names on the side, and then whatever the instruments is. So like I'd say like this is B, C, F, V, and then O for oboe, and then just the initials. Maybe it doesn't matter. Now J knows how to play the bassoon and the clarinet, so he can connect it to there and there. Okay, and then K knows B, and V, so B, and V, and then you just repeat this all the way down. You're just reading off, and that is your graph. That should be fine. Okay, for BII, it's saying Nish arrives late to the rehearsal. Each of the four musicians is already playing these instruments. Okay, well, explain how there is no instrument available that Nish knows how to play. If J is playing the clarinet, right, that means everybody else that's connected to the clarinet must have their connection be lost, right? So this connection from L to C goes away, from M to C goes away, and those are the two other ones. And then for this connection, K is the only one playing it, so KO stays in. So MO goes away and NO goes away. And then you just repeat that for all of them, and you'll notice that afterwards, once you get rid of all of those unnecessary arcs, after people have already started playing their instruments, you'll notice that the only instrument left is the bassoon, okay, which Nish doesn't know how to use because N doesn't connect to B. He doesn't know how to play that instrument. When Nish arrives, the rehearsal stops. When they restart the rehearsal, he's playing the flute. Draw all possible subgraphs of the graph to show J, K, L, and M can be assigned a unique musical instrument that they know how to play. Okay, so this is just the initial graph that I've copied over. Okay, and we're told that Nish is playing the flute, so I'm just going to give him like sole access to the flute. So N here, I've removed him, and then I've removed F as well because that's what he's doing. And then anything else that would have been connected to F is irrelevant because they can't take that instrument because he's playing it. Okay, so this is one possible one. Okay, and then you could also have this here because J can play either B or C. Okay, let's just say he plays B. Okay, in which case K would have to play or V. Okay, I've said let's let him play in which means that L is just going to stay with C because that's the only one it can connect to. L is always going to be playing C, and then M must connect to V because K is already taken and C is already taken by L, so M can't get there. The other option is obviously J. Instead of connecting to B, it could have connected not to C because that's only L. That's L's only option, and not to because there's just no connection there. Wait a minute, sorry, no. Oh no. Okay, yeah, sorry, no. I'm looking at K, sorry, because J going to B is the only possible option. J can't ever go to C. So J has already played all their possible instruments. So now we're moving down to K to see what he could possibly play. He can't play B because that's for J. So he could play O or V. We've already looked at the case where he plays O, so we'll look at the case where he plays V. Okay, and then you just fill in the rest of the graph you as normal. Okay, and these are the two extra graphs that you get to show that they each play a unique instrument that they know. Here we've got modular arithmetic, and we've got a Cayley's table, mod 4. 0 times 0. This here is just going to be 0, 1, 2, and 3 because these are all. Oh no, sorry, just 0, 0, 0, 0, 0. Obviously, because anything times 0 is 0. It's similarly here for the same reason. So just fill that in. And then this is just going to be 1, 2, 3. So I'll fill that in, and then you can kind of tell that it's going to be symmetrical, but this here is going to be 2 and then 3. So I'll fill that in. This 2 times 2 is 4, but 4 mod 4 is 0 because the remainder after you divide, not necessarily divide by 4. Yeah, after you divide by 4, the remainder becomes 0, so that's a 0. Then 2 times 3 is 6. 6 mod 4, and we take away 4 as many times as we can. That gets us to 2. 2 times 3 is 6, same thing there. 1 times 3 is 3, same thing as there. And then 3 times 3 is 9. 4 goes into 9 twice, remainder 1, so that's the one there. Here we've got a set S is defined as ABCD, and we've got an incomplete Cayley table, and we need to complete it. Okay, if we know that A gives us B, and AB gives us A, because it's commutative, we know that BA or AB given as A, this here, AB, must also just be an A. And similarly, because AC here, we don't know what it is, we know that AC gives us A, and so CA, or whichever way you want to say it, would also give us A. Okay, and then here, AD or DA gives us C, so then just flipping it around, DA or AD will give us C as well. And then BC here is D, so CB would be D as well. And then C times D is going to be the same as D times C, and D times C, C times D is D. Okay, and then finally we've got BD here, so BD here, that's a C, so you can put that as a C. Determine whether the binary operation this is associative when acting on the elements of S. Now, to be associative, if you have A dot B dot C, it's the same thing as if you were to do A dot B first and then dot C after it. Okay, so we'll just calculate this first of all. B dot C is going to be D, so this just becomes A dot D, and A dot D is C. So that's fine. And now we'll check A dot B first and then dot C. So A dot B is A, and then dotting C. So A dot B is A, so yeah, so that's A dot C, and then A dot C is A. And these two are not equal. Because they're not equal, that means that this is not associative when acting under S. And you only need one example to show that something is not true. So that's fine. Here we've got this graph here, and we want to find the least possible time for the scale to cut grass on all 15 paths in the nature reserve. Because she wants to get across all edges in the least amount of time, what she wants to do is ideally repeat as little edges as possible. Now, the easiest way in which you can do that is if the graph is Eulerian. Okay, but this graph here, we've got one odd node here, we've got another one here, and we've got another one here, and we've got another one here. Okay, because it doesn't have exactly two odd nodes, the graph isn't Eulerian, nor is it semi-Eulerian. Okay, so it's just not Eulerian at all. Okay, so what we need to do is make the graph Eulerian, because if we do that, then she'll repeat as little edges as possible, and then get back to the start. Okay, so we just need to know of the odd nodes. Sorry, what does she need to repeat? And then if she repeats that, we want that to be the least amount. Sorry, so she wouldn't necessarily repeat an edge that takes forever. She would repeat the edges that take the least amount of time, because then she'd cut the grass as fast as possible. We've got the total length is 1465, and the mower moving at 7 kilometers per hour. So the odd nodes, I'd already mentioned them. It's these. So what we want to do is just pair them up and see what edges we can repeat. So we could have EB and then GH. We could have EG and BH. We could have EH and BG. And that's all. That's everything we can have. A quick check is doing 4 choose 2. Anyway, so EB plus GH. EB is from here to here. We need to find the shortest path. It's definitely not going to be anywhere to the left. Okay, it could be this one, so 210 plus 45 gives us 255. Let's see if we can make it any quicker. This is 100, and then this is 95. So 195 looks like it's the shortest so far. So we've got 195, or we could have 160 plus 50, so that's 210. It's not very short, so E to B must just be 100 and 95. And then GH, so the shortest from G to H is just going to be 50. So we have 195 plus 50 to get us 245. Okay, and then E to G, where is E? E to G, so that's 140. This way is going to be 150, I think. Whatever it is, it's definitely longer than 140. So here we've just got 140 as being the shortest from F to G. Oh, it says E to G, sorry, not F to G. Where is E again? E to G. Okay, so 90 plus 140, so that's 230. Or you could have 210 plus 60 is 270. That's longer, so we don't want that. 90, and then this way is longer, yeah. So we just want 90 plus the 140, so that will be 230 from E to G. And then B to H is going to be 45 plus 65. This way would take too long, and any other way would be too long. So that's just 65 plus 45 plus 140 plus 90. That gets us 340 apparently. And then E to H plus B to G. E to H is where is that? So that's from here to here. 90, and then 140 is probably going to be the next quickest, I think. No, because then we do 140 plus 50 here, so this becomes 190. Although this here would actually be quicker, so we would do 90 plus 75 plus 85 to get EH, and then for BG we would do 45 plus 60. Looks like it's the shortest. This would be too long, so yeah, we'd do 45 plus 60 plus 90 plus 75 plus 85, and that gets us 355. Now, which is the shortest? It's clearly this one here. So if we repeat this one, then we can make the graph Eulerian. Would it be Eulerian or semi-Eulerian? I'm not sure. Anyways, because this is the shortest, we're going to want to repeat this one. So we'll do all of the 1465 meters, and then we're going to repeat this one. So that's plus another 245. So our shortest path, our shortest distance in meters becomes this plus this, and that gets us 1710. Because we obviously do 7 kilometers per hour, that's this here is just 1.71 kilometers. So we do 1.71 kilometers per some X hours, but 7 kilometers per 1 hour. And so to get from here to here, we do times by 1.7 over 7. So we do 1 times by 1.7 over 7 to get X, which is 0.244 hours. You can do this in another way, obviously, but that's just how I did it. This is your answer. Brooke visits every information sign on the nature reserve to update them starting and finishing at the entrance. For the 8 information signs, the minimum connecting distances of the grass paths is 510 meters. Determine a lower bound for the distance Brooke walks to visit every information sign. Because she's trying to visit now every node, not specifically every edge, this is going to be the traveling salesperson problem. Is it? Yeah. Obviously, yeah, it is. This here must be the upper bound, I think. The minimum connecting distance. Oh, actually, no. This is just a different piece of information. Now, to do that, to do the traveling salesperson problem, you calculate a lower bound and an upper bound. The lower bound is calculated by first removing. Sorry about that. The lower bound is calculated by first of all removing all the edges to the start node, and then we perform a minimum spanning tree algorithm like Prim's or Kruskal's on the remaining on the residual tree, and then we add the 2 shortest edges back. So to determine the lower bound here, I've just put this again. So the 2 smallest edges from A are going to be where is A? It's going to be 45 plus 50, so we'll just leave that there, and then plus the 510 because they've already performed the minimum spanning tree after removing A. So that becomes we add the 510 that they've already calculated to get a 615, and that will be our lower bound. Using the nearest neighbor algorithm starting from the entrance, determine an upper bound for the distance Brooke walks to visit every information sign. Now, the nearest neighbor algorithm, the way it works is you start at your node, and then you just continuously pick the next shortest one. Okay, so we start at A, the next shortest is B, okay, and the next shortest from B, you can't go back across A or B, so the next shortest from B will be C, and then afterwards it'll be D, and then afterwards it'll be E, and then afterwards it'll be F, and then after that it looks like it's going to be I, and then H, and then G, and then A, and that's fine because we need to get back to the starting node, so we just take that journey back. You add all of these up together, you'll get 615 meters. Now, I think they ask about it here. Oh no, I don't think they did. Okay, never mind. Okay, anyways, so there's 8 signs here. Okay, and let's see what it says. They walk on grass paths at an average speed of 5 kilometers per hour, and they start from the entrance at the same time. Use your answers from A and B to show that Ashley and Brooke will return to the entrance at approximately the same time. It takes them 615 minutes to travel to each vertex and back, and because the lower bound is exactly equal to the upper bound, that must just mean 615 is the exact distance. It's actually a case of the traveling salesperson problem where you've got a solved graph. So we've got 615 minutes, right, and it takes us 5 kilometers per hour. There's 8 signs, okay, and that corresponds to. Sorry about that, I got interrupted again. Anyways, so 8 signs taking 8 minutes because they stop at each one for a minute. It takes 650 meters to travel to each vertex, and it takes this many hours to actually mow all the paths. So I just want to find first of all how long it takes to travel this. So this is 0.615 kilometers. At an average speed now of 5 kilometers per hour. So just work out whatever that is in your preferred method. So that's 0.123 for me. With my method, sorry. This here is 0.133 hours. Just 8 minutes if you just convert that. Plus the 0.123 here. Well, I just added that to that. And then plus the 0.25. Oh, sorry, no, that just equals 0.256. Never mind. Yeah, and that's approximately 0.244 hours, which is what we calculated initially. So it is approximately the same time that they return back to the start. Say an assumption that you've used in part of CI. With this, you're just putting down stuff like this, like they don't take any breaks. There was no obstructions in the road. They didn't run out of paint, maybe, or whatever. I can't even remember what the context of the question was, but something related to the context, ideally. Here we've got some game theory. This is the payoff matrix for Ali because it's showing his possible winnings, but we want to show it now for Bex. Now, when you have a payoff matrix, it always represents the scores of the person that's on the rows. So in this case, Ali, because he's on the rows. If we want it to be for Bex, we just need to swap Bex and Ali. But you have to be a little bit careful because if Ali, say, gains 2 points, that means Bex loses 2 points. So this here A1, B1 would actually, instead of being 2, it would become -2 because Ali scoring 2 points means Bex loses 2 points. So that becomes a -2. And similarly, A2, B1, so that would be here. This would, instead of being a -4, instead of Ali losing 4, that's the same as Bex gaining 4, so that would be a +4. And then you just repeat that for all of the other ones. Hopefully my explanation was sufficient for the rest of them. And you're just left with that. Explain why the payoff matrix for Bex can be written as this. Whenever it says something like this, you want to look at the idea of dominance and see what specific strategies dominate each other. Here, if you look at B3, it's dominated by B1 because in every single category, B1 is just better. Here you're losing the least, here you're gaining more, here you're losing the least, here you're gaining more. So B3, you should actually just never play that because B1 is automatically always better than it. So B3 is dominated by B1, so Bex should never play B3. And so you can just remove that row entirely, and that leaves you with this, right? But also, for Ali, because you notice they've only got 3 columns here, we've got 4. A2 is dominated by A1, right? Because in this case here, 4 is greater than -2. Sorry, no. I'm still thinking about it in terms of Bex. The reason why A1 is better than A2 is because this here is showing the payoff matrix for Bex, right? And now Ali, what he wants to do is, if you're looking at Beck's perspective, Ali wants the most negatives, right? So he'd prefer to have -2 over 4 because -2 is a -2 for Bex, so a +2 for Ali. If this was a 4 here, that's the -4 for Ali, not a +4 for him. So he'd actually prefer to have the -2 over the 4. He'd prefer to have the 1 over the 2 because that mean in this case here he's only losing 1 instead of losing 2, and this in this case here he's only losing. Sorry, no, he's gaining 3 instead of gaining 2, so he would prefer this. So in all categories, A1 is just better than A2, so he should just never play it. And if you get rid of this and that, you're just left with this. The game does not have a stable solution. Bex plays her optimal mix strategy. Find the value of the game for Ali. Now, this is what the matrix reduces to. Right, and we're just having a look at what would Bex's strategy be if Ali played, say, A1. Okay, say for example, let Bex, imagine Bex plays B1 with a probability of P, right? That means she plays B2 with a probability of 1 - P, right? It's just, if you were not to play B1, you'd play B2 with a probability 1 - P. And so if Ali plays A1, okay, then Bex's expected payoff would be -2p plus 1 lot of 1 - P. Okay, it's the probability times by the amount. If you have a probability times by an amount, you know, from regular AS maths, that's just an average, or the expected amount if you do statistics for further maths, which I'm sure many of you do. And then similarly, if Ali plays A2, then Bex would have 0 times by P plus -1 lots of 1 - P. Okay, and then you repeat that for this should say A3, not A2. That would be 3p minus 2 lots of 1 - P. And then finally, I just simplified each of these, and I've put them in different colors just to make them a bit easier to understand. And now what we usually do in these game theory types of questions, we always first of all try to reduce it to a 2-by-n matrix. Okay, 2 by 2 is the easiest to work with because we know that we just need to set those 2 equations equal to each other. But here, if we've got 3 or more equations, then the best thing we can do is just graph it. Right, so we'll draw our diagram. It goes between 0 and 1 because that's what the probability lies between, and then we'll just graph p minus 1. Right, y-intercept of -1, and it has another intercept here at 0. If you just plug in different values, you can just work out what it's supposed to look like. and then similarly draw it for this red one here. It's going to have a negative gradient, so it should look something like this, and a y-intercept of +1, and then here y-intercept of -2, but positive gradient that's very high, so somewhere like this. Okay, and finally we want the highest, like the highest expected payoff for Bex, right? Because then that would be their optimal mix strategy. They're not trying to gain as much points as possible necessarily. They're just trying to lose as little as possible, right? And that's just going to be the highest point that's beneath or equal to a specific point on all of these graphs, and that would be this one here, p-1 and 3p-2. So that would be here, right? Because that's the highest that's beneath all three. So that means this equation here and this equation here, we set them equal to each other. You'll get 4p equals 2, so p equals a half, and that means that Bex should play b1 with a probability of a half, and b2 therefore with a probability of a half, i.e. the rest of the time. Okay, and his expected payoff is just going to be, if you were to plug in a half into either of these equations, say if I use this one here, a half -1, you'll get minus a half for Bex as his expected payoff. But if Bex's expected payoff is minus a half, and we're looking for Ali's expected payoff, if Bex loses a half, that means Ali gains a half. So that means Ali's expected payoff is going to be a half. The reason why we set these equal to each other is because of an idea of indifference. We don't want Bex to say prefer one strategy over the other, because if she does, hypothetically Ali could pick up on that and then realize that she's favoring a specific strategy over another one, and then he would pick therefore a different strategy to counter that. So by setting those two strategies equal to each other, we're saying ideally we want the exact same expected payoff for each of them, because in that case then we would just pick between them according to our probability, instead of picking between them based on what we think we might get as an expected payoff. Anyways, I hope that made sense. The answer is a half for Ali. That's the entire paper. Thank you for watching.